Hello everyone. In this video, I'm going to go over section 3.1, conditions of equilibrium of a particle, section 3.2, the free body diagram, and also section 3.3, coplanar force systems. So this is an example of 2D or coplanar forces system. If the whole assembly is in equilibrium, when we say equilibrium, then the particle is also in equilibrium. To determine the tension in these cables, in all of these cables for a given weight of the cylinder, you will need to learn how to draw a free body diagram and apply the equations of equilibrium. Free body diagram, one of the most important tools that we're going to learn, and we have been practicing a lot of that back in physics. We will do quite some more in statics. And what is it? It is a drawing shows all the external forces acting on particle and why it is the key to be able to write the equations of equilibrium. Without the free body diagram, we cannot write our equations. So only free body diagram first, and then we write our equations. With the equations, we can solve for our unknowns. For example, if I have cable DA, AB, that is holding at this point A and holding this cylinder down below. So imagine the particle, we want to isolate the particle away from everything else. So looking at particle A only. Looking at particle A only, I have three forces being applied to A. I have force D, so in other words, the tension from DA that is pulling A toward the left. And I also from this cable AB that has a tension FB pulling the particle toward the upper right corner. And then also the weight of the cylinder that is pulling particle A down, which is the weight, the amount of force pulling down from the cylinder will be the weight of the cylinder. So we're going to show all the forces acting on the particle. Active forces, they want to move the particle, and reactive forces, they tend to resist the motion. We're going to identify each forces and show all the known magnitude. Like for example, we know the weight that's pulling down is going to be 40 kilogram times 9.2, which is 392.4 Newton. Okay, so that comes from this number right here, comes from 40 times 9.8 gives you the Newton. 40 was given, kilogram is given. We converted that kilogram to Newton, convert the mass to force. Okay, so identify all the forces that we know, show their magnitude if we know the magnitude, show the direction if we know the direction, show all the unknown forces and direction as well. Now, in the last video, we talked about how forces are vectors. When we're adding forces, vectors together, it's not simple algebraic addition. It's not. So all the forces here, we can break them down into the horizontal component and the vertical component. And then we say in general, for a particle in equilibrium, summation of force equal to zero. And that also means summation of force in each direction equal to zero. So in other words, the sum of the forces on the horizontal direction equal to zero, sum of all the forces on the vertical direction equal to zero. This will give me the overall summation of all the forces equal to zero. Okay, so keep going. So these forces right here, I am going to break down my FB into the vertical component and the horizontal component. So on my diagram, it's going to look like FB. Over here, I have a FBY. Okay, and then over horizontally, I have a FBX. Now, we talked about in the previous slide that horizontally summation of all the, so what I meant to write is FBX over there. So when I talk about, in the previous slide, we talk about FX, summation of all the forces, horizontal direction needs to be equal to zero. So there you have your FBX, which is FB cosine theta, pointing to the right, positive, and then FD pointing to the left, that will be negative. So these two are the only two forces horizontally. Okay, again, FBX, it will be FB cosine 30 because 30 degrees given. It's positive because it's going to the right. And then your FD is negative because we're going to the left. And then your Fy component, you have your FB sine 30. FB sine 30 is the Y component coming from the B. And then also on the vertical direction, you have that 392 Newton comes down, which comes down from the weight of the cylinder. I got two equations and two unknown. We have this written. Two equations and two unknown. Unknown number one, FB. Unknown number two, FD. These two equations and two unknowns, we can solve them. Okay, there we can find out what are the tensions on the cable DA and cable BA. Spring system, spring system, spring force equals to the spring constant times the deformation of the spring. So, in other words, there are different size and strength of the spring. Some springs are harder to pull, and some springs are lighter to pull. So, different spring is going to have this different spring constant. So, in order to find out how much force coming out from the spring, we need the spring constant from each force from each spring. Okay, spring constant multiply how much the spring is being deformed depends on 1 inch, 2 inches, or 3 meters, etc. So how much deformation are we talking about? Also affect how much spring force we have. Spring force is depend on spring constant, and it also depends the deformation of the spring. So F equals K times S. Cables and pulleys with a frictionless pulley and cable, T1 equals T2. So, in other words, it's the same cable. It's the same line going from here to here, going from here to here. It's the same cable. So, any forces on the same cable, they experience the same tension. T1 equals T2. Cable can support only a tension or pulling force, and this force always acts in the direction of the cable. Now, smooth contact, when we say smooth contact, it means no friction. Okay, no friction. But since we have a contact, there will be normal force acting to support the rigid body. So we have a tension pulling up 20 degrees away from the vertical direction. And then over here, I have the second diagram down below. You have the weight that's pulling down, and you also have a normal force. That's what does N stands for. You also have a normal force that's supporting the rigid body. That normal force come out from the surface that is 30 degree from the horizontal direction. So there are three forces: concurrent, tension, weight, and a normal force. These three forces help the particle reach an equilibrium. When we say equilibrium, back in the few slides back before, we talk about we're referring to all the forces, summation of all the forces equal to zero. And you can also say summation of all the forces horizontally equal to zero, summation of all the forces vertically equal to zero. Example number one, this is similar to the very first example that we seen. We can find out what's going on at point A. So we're going to draw the free body diagram at point A. At point A, you see three forces. You have the tension from cable BA, tension from cable CA, and there's also the weight of the box pulling down from point A. So three forces there: FB from the cable BA, FC from the cable AC, and then you have the weight pulling down. We can break down our forces, FB and FC, right, into the horizontal component and the vertical component. FC, the same thing, vertical and horizontal. And we know that we can write FBX, FBY, FCX, FCY. And then later we pull all the X component together. This one right here is your FBX because it's going toward the left. It's got a negative value. FCX, this is your FCX. Okay, it's going toward the right direction and it's positive. And then your Fy, you have Fby going up, okay, positive, and you have your Fcy going up, positive, and the only force that's going down vertically, it's negative 550 coming down. Okay, so putting them together, set them equal to zero. Summation, putting all the X together, set that equal to zero. Putting all the Y component together, set that equal to zero. That will give me two equations and two unknowns. We can solving for our value FB and FC. Example number two. Okay, we're looking for the tension DE, EA, and EB. So we're going to draw our free body diagram about point E. What I want to point out is that we have a pulley over here. Sorry, did not need that. Let's do that again. Let's try that again. So we have a tension from this cable going over this pulley. Okay, you know what I mean? You keep on giving that line. But the tension from EB and tension from CB is going to be the same. It's both pulling it because they use the same cable. And that tension will equal to the weight of the cylinder. So you take that 40, multiply by 9.8, that will give you the weight. That will give you the weight of the tension from BC, and that is the same tension as your EB. So that's why tension of EB equals to 40 times 9.8. Okay, so now we're breaking down the only force that we break. So DE horizontally to the right, EA vertically going down. No need to break. They're already on the x-axis and the y-axis. We're going to need to break our force EB horizontally and vertically. EB, I have a horizontal component, which is 40 times 9.8, right? That's the original EB, times cosine 30 degree, positive going to the right. That's that part. So that's the x component of your TEB. And then your TED going to the left, negative. Okay, putting the x together, set that equal to 0. Similarly, we're going to take the y component of that EB, which originally EB you got 40 times 9.8, and then sine 30 gives me the vertical component. And then on the other side, you have tension EB coming out from the weight of the cylinder A. Okay, so that's your EB equal to, set that equal to 0. Again, we got two equations and two unknowns. We're solving for the tension ED and the tension in EB. Okay. Another group problem here. So we're gonna do, we know this lamb, we know the mass of the lamb is 20 kilogram. Okay, over here we is 20 kilogram. We're gonna convert it into Newton by doing 20 times 9.8. We want to find the forces in each cable. We're going to draw the free body diagram about point D. We're going to do it about point D, and we're going to see your forces CD, FCD pointing to the left, and then tension DE pointing at an angle, and the weight coming down. Again, over here, we are going to break our DE into the vertical component and the horizontal component. DE sine 30 gives me the Y, okay, going up positive Y. And you have that 20 times 9.8 coming down, negative value coming down, pulling down. So that's the summation of all the forces along the Y direction. And then along the x direction, you have your CD to the left, FCD to the left, negative, and you have your FDE to the right, FDE cosine 30 going to the right. Two equations and two unknowns. Again, we're solving two equations and two unknowns to get the value of tension DE and the of tension on the CD. And then keep going. We're going to do a free body diagram on point C. On point C, we see the tension from the cable AC. We see the tension from cable BC, and there's also the tension from CD. Again, we're going to break our AC into the vertical component, horizontal component, BC, horizontal, and vertical. And then later, we're going to do all the summation of all X component together, summation of all the Y component together. And again, two equations and two unknowns. We're solving for FBC and FAB. Okay, hope this video helps you. That's all I want to share with you today. Thank you for watching.